We will discuss why PI-based CDR before, and it's obvious a high linearity phase interpolator PI is a must to achieve a good jet-out CDR. But recently, the high linearity PI has become another high demand. Do you know which area for the emerging high demand? Correct. The interleaf ADC needs multi-phase output. For example, 4, 8, or 32 phases PIs are the output of each PI in an ADC-based PAM4 receiver, which is also require a very high linearity phase selection for 112 gigabit per second over 224 gigabit per second high speed and low power series. So we may need to understand what PI topologies we could leverage to achieve a high linearity and low power PI. The first one is the CMOS PI, which should have the best linearity as a simple CMOS cells. Is that true? From my understanding, if we do have a resistive load and a CMOS output, the output phase should be linear enough, assuming the current weighting is linear enough between the two superpositions. If not, you may still have ways of adding the source degeneration to enhance the linearity over a wider input swing range. Therefore, the CMOS PI should probably provide you with enough linearity. How about the power? Is it possible to always have low power for all frequencies? Good question. Yes or no? If we don't scale the current and the resistive load at the low frequency, of course, the power overhead could be too much. In addition, if we don't scale the resistive load, the slew rate of the output waveform could be too fast to keep good linearity. So, to scale the resistive load to greater resistance and keep the proper operating point bias for those transistors must scale down the current as well. Therefore, the CMOS PI of both high linearity and low power seems the best topology for wide data rate series. Could you tell me why you would need another topology? Think about the output swing level image for 5 seconds. Correct. The output swing of the CMOS PI is not rail to rail, which benefits the low dynamic switching current and faster switching. But that would limit other blocks connected from and to must be in a CMOS level as well. For example, the compactor over the sampler must be a CMOS latch topology, such as the CMOS PI output clock can drive the CMOS sampler directly. What happened, or what should we do if we like to use the strong arm latch or the sense amplifier kind of rail-to-rail compactor to the sampler? Bingo! If you connect a low swing output clock to drive the rail-to-rail CMOS latch, then the clock will not turn on or off properly. To make the signaling compatible, you must apply any CMOS to CMOS conversion, which seems doable. But any issue with the signal level conversion block from CMOS to CMOS? Correct. Phase distortion. From a low swing converted to the rail-to-rail CMOS, the phase distortion could reduce the phase linearity, which conflicts the original motivation of a high linear CMOS PI. Then, what can we do? Correct. As we discussed, the voltage mode driver in a CMOS topology. We could also apply the CMOS or voltage mode for the PI, which would inherently be comparable with the strong arm latch CMOS level without any need for the swing level conversion. Also, from the power point of view, the voltage mode PI may have the same advantage as CMOS CVF power, which scale well with the frequency simply without any extra tuning like the CML PI. But can the CMOS PI have a good linearity over frequency easily? Before answering it, could you please think about the slew rate image for 5 seconds? Bingo! At a low frequency clock, the slew rate tends to be much faster and result in a square wave-like waveform. In other words, the rise or fall time is much shorter than the clock period. Then the transition time of the interpolated waveform phi z is distorted or nonlinear between different waves from the input waveforms phi x and phi y. After a few buffers of the phi z, the output phase phi out shows the nonlinearity phase stepping, very small phase resolution, and a small and large phase cone, while a big phase spacing at the middle of the phase cone. Virtually, you will realize that this distorted phase versus phase cone will not work for high-speed SerDes. What should we do? Press, think about another slew rate image compared to a high-frequency clock for 5 seconds. Very good. At a high-frequency clock, the slew rate tends to be much slow and result in a sine wave over the triangle wave-like waveform, similar to the one in the CML. In other words, the rise or fall time is close to the clock half period. Then the transition time of the interpolated waveform phi z is equal phase between different waves from both input waveforms phi x and phi y. After a few buffers of the phi z, the output phase phi out shows an equal phase stepping between the phase cones. Then the slow slew rate of the voltage mode PI has a high linearity. The question for you is, how can we slow down the slew rate over different clock periods or frequencies, such that the phase linearity could be manifested over frequencies? Think about the supply or overdrive images for 5 seconds. Correct. From Microelectronics 101, you should know the overdrive or supply of a CMOS inverter may determine the current strength or the transition time of the charge or discharge activity. Therefore, we could define what the transition time or the slew rate of the interpolated element needs to be, then just to scale the supply to the corresponding slew rate in the design. The straightforward is to use any ring-based oscillator as a replica to generate the proper supply voltage over different clock frequencies in the same ratio of the slew rate and clock period, which should be good approximation. Here are a summarized image showing you why you need a high linearity phase interpolator PI with a low power. First of all, a high linearity PI is a must for CDR to achieve a good J-tau. Also, for interleave ADC, not only a high linearity PI is a must to achieve the best SI and low bit array, but also a low power is a must to make sure the power overhead and the PI don't blow out quickly in the 224 gigabit per second painful AEC-based series. The two most popular high linearity phase interpolators PI are the CMOS PI and the VMPI, since the series must operate at a very wide range data rate from 1 gigabit per second to 224 gigabit per second. The linearity and power of either the CMOS or virtual PI must be scaled over frequency. For the CMOS PI, both the resistive load and current must be scaled or switched over frequencies to maintain linearity and scale power properly. On the other hand, the virtual PI must scale the supply over frequencies to maintain the slew rate ratio compared to the clock period, such that the interpolated phase linearity can be maintained over frequency. From my experience, with the help of a replica ring-based oscillator, the virtual PI may easily keep good phase linearity and low power through the CVF current at the same time over a wide range of operating frequencies. Also, the regulated power supply and the virtual PI may help mitigate its inherent poor supply rejection compared to the CMOS PI. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.